Next video. And in today's video, we're going to be learning a little bit more about neutralization reactions between acids and bases and how to perform titrations. I will have gone over some of this in class by the time you have watched this, but this is going to give you a little bit more detail about the idea behind what a titration is and how it works. So acids and bases react together. We saw this in the first video. They react together, and they do so, we've seen this a long time ago, in a double replacement reaction. And when the double replacement reaction is between an acid and a base, the products are always going to be a salt and water. Now, a salt isn't just sodium chloride. A salt is any ionic compound that does not contain H plus, hydroxide, or oxide ions. And while some of those may be ionic compounds, they're not considered to be salts. So, for example, our simplest kind of salt reaction, neutralization reaction, is taking hydrochloric acid and sodium hydroxide. So here's our double replacement reaction. If you remember, we had our AX and our BY, and we ended up having to rearrange that. The A went together with the Y, and the X came together with the B. And when the A comes together with the Y, we make HOH, and HOH is just another way of writing H2O, and that's a liquid. And then when we put together the B and the X, and remember, the B has to go first. It always has to be the cation, then the anion. We're going to make sodium chloride. Now, sodium chloride, sodium is a +1, chloride is a -1. So a 1-to-1 ratio, and that's going to be an aqueous compound. In these double replacement reactions, the cation, there's the cation, always comes from the base. And the anion, in this case the chloride, always comes from the acid. And so you can kind of think of a salt as the product of an acid base neutralization. Interesting to think, neutralization, that you can take hydrochloric acid. You wouldn't want to drink that. I certainly wouldn't want to. It can destroy your stomach, your esophagus. Sodium hydroxide, same thing. You mix them together and you make good old salt water, which you wouldn't be very tasty, but you could drink it. Of course, I would not recommend that because you have to have the stoichiometry just exactly right. And we'll be talking about stoichiometry again in a moment. Speaking of stoichiometry, we have another reaction, this time between sulfuric acid and potassium hydroxide. Now, I've already got the 2 in place there, which is going to tell you something about balancing this. Now, when you balance these, and when you write these reactions, you always have to write the water. And the whole idea here is we have H2. Now, H2 is not a compound. There's no H2 ion. If you remember, that means that we have 2 H ions, H plus ions, to go together with the sulfate, which is a -2 charge. So when you put the products together with this, you've got to keep that in mind. The products are going to be, again, water, and the water is going to come from the 2 H's and the 2 OH's. Now, don't write anything like this. If I see something like H2OH, we've never seen that compound. Don't write anything that looks silly like that. This is not a Bronsted acid-base reaction. We're not going to have, what happened to my, we're not going to have HKOH. We're not doing that. So neither of those are going to be something that you're going to want to do. Instead, we're just going to take the acid and the base, and we recognize the acid and the base because of the H in front and the OH here, and we're going to make HOH. I'm going to write it as HOH again because it's going to be easy for you to see how to balance this in a moment. And we're going to put the potassium together with the sulfate. And it looks like an R, doesn't it? Now remember, sulfate is 2- charge, and with potassium as a 1+. That's why we need to write K2SO4, and that's why we have the 2 here. We also have 2 hydrogens. That means we have 2 OHs, and 2 hydrogens and 2 OHs make 2 HOHs. We're going to have 2 waters. And that's going to be something that you'll always see, that if you have a subscript 2, or if you have a subscript 2 on the hydroxide, you're always going to get whatever that subscript is in the amount of water. Oh, and something's missing here. The potassium sulfate should be aqueous. So you'll have some practice on that during the homework. So acid-base neutralization reactions are pretty important reactions for a number of reasons. Sometimes you need to neutralize spilled acid. You hear about tanker cars full of sulfuric acid being derailed, and they have to neutralize that somehow. Our lab this week is going to evaluate vinegar. And vinegar is a weak acid, and we're going to use the titration to see whether the bottle that tells us that it's a 5% solution of vinegar, of acetic acid is actually the chemical, whether that's actually correct. This would be a quality control kind of reaction that you might need to do. So what we're going to do in a titration is we're going to use that acid-base neutralization reaction where one concentration is known. So you're going to know the concentration of either the acid or the base. It doesn't matter which one. In the case of our lab, we're going to know the concentration of the base. And we call that being standardized. I will have taken care of standardizing the base for you, or I would have anyway if it was a real lab. And what we're going to do is we're going to find the concentration of the other. And remember, that concentration is unknown, or we're not sure what it is. You can titrate the acid with the base or the base with the acid. It doesn't matter which one. In this case, like I said, we're going to know the base concentration, or you can go the other way and put the acid concentration, be that one that you know and don't know the base concentration. And when you titrate, you're going to titrate to what's called the equivalence point. The equivalence point. Now, when you say an equivalence point, something must be equivalent, right? Call it EP. What's equivalent? The correct volumes of acids and bases are mixed. So we've mixed the acid and base reaction together. You'll see in the titration video how we're going to actually mix them together so that when you hit the equivalence point, the moles of the acid, the moles of the H plus that you've added from the acid has to equal the moles of the OH minus that you've added from the base. And that's where stoichiometry is going to come in. What we do is we monitor the pH. We're going to talk about pH tomorrow. pH is basically how acidic or basic the solution is. Now, these are two clear colorless solutions. When we mix acids and bases, acids are clear and colorless, bases are clear and colorless. How are you going to know when the reaction is over? You have to use an indicator. This indicator is an organic dye that changes color. So this is a dye that can have it can have two different colors. One color when it's acidic, one color when it's basic, and it changes color at a certain pH. And the pH that you want to change color at is called the end point, or the pH that where it changed color is the end point. We'll get down to that in a moment, the end point down here. If we have a strong acid and a strong base, now we didn't really cover strong acids and bases. HCl, so this would be, for example, HCl and NaOH. And in a titration, you always have one of them that's going to be strong. Otherwise, the titration is not going to work very well. So HCl and NaOH. This case, when they neutralize, they do make a pH that's exactly equal to 7. And that's a neutral solution. Now, even though the next two are not neutral at the at the equivalence point. They're still called neutralizations because we've essentially gotten rid of the strong acid or strong base. So a weak acid and a strong base. This is what you're going to be doing in lab. So this would be acetic acid, HC2H3O2, and sodium hydroxide, for example. That would be a strong base and a weak acid. Because of the strong base is going to make the solution at the end basic, and because it's basic, that's going to have a pH that's greater than 7. And if we turn it around and at a strong acid and a weak base, this would be something like HCl combining with ammonia. And I'm not going to have you do that because that's a little tricky. That would have a pH that's acidic because the acid would make the solution acidic at the equivalence point. So the end point is where you're actually going to stop the titration. Now, ideally, you want to get the end point as close to the equivalence point as possible. But what's going to happen is from the equivalence point, you're going to have to add one more drop of that reactant, because at the equivalence point, you're right in the middle and you don't know. In fact, with the the dye, the indicator that we use, that's called phenolphthalein. That's a tricky word. Phenol, phthalein. Yeah, there it is. I think it's going to be in the lab handout, so don't worry about it. And I'm never going to ask you to spell it. Don't worry about that either. You won't get a color change until you add one extra drop of the known reactant. That's the standard solution. And in our case, that's going to be our base. And the indicator is going to monitor the pH. So the indicator is going to change colors at a particular pH. What pH does it change at? That's going to be the endpoint. And what we're going to do is use something called a burette to measure the volume. So you want to measure the volume of the standard solution. And when you measure the volume of the standard solution, you can then use stoichiometry at the end point to determine the concentration of the unknown solution. So here's how that works. So as I said, we're going to know the molarity and the volume of one solution. Again, that's going to be our standard solution. And again, in our lab, that's going to be the base. And we're going to know the volume of the other solution. That's the unknown solution. We can call that the analyte. This is what's being analyzed, or analyte. And in our case of the lab, this is going to be our vinegar solution. With acetic acid, HC2H3O2, in it. And so we're going to determine the molarity of that other solution. So, for example, if I give you this reaction, nitric acid and potassium hydroxide, making water and potassium nitrate. There's our salt. I want to know what the concentration is. So my unknown is the concentration of the, let me circle the whole thing, of the KOH solution. If I have 25 milliliters of KOH, so this is unknown, I don't know this one, but this is the volume that I have, requires 11.5 milliliters of 0.500 molar nitric acid to neutralize it. Okay, so we did these kinds of equations, these kinds of stoichiometry back in chapter 15 when we wanted to know what the unknown concentration was. And I broke it down into two parts. I broke it down into first, the moles of your known solution getting to the moles of your unknown solution. And then the second step was the KOH. So always think about, I have this known solution. If I know the volume and I know the molarity, I know the known solution. So there's the known solution here. This is the nitric acid, HNO3. That's on the next line, but I think I want to have it here just to show you. So the first thing I'm going to do I'm going to think about this. I need to go from milliliters of the nitric acid to moles of the nitric acid. I can do that because I know the molarity. And then from there, I'm going to go to moles of my KOH using stoichiometry. So here's how that's going to work. We take the volume, the 11.5 milliliters of the nitric acid. We use our little 1,000 milliliter trick down here and multiply that by 0.500 moles. And those are both of nitric acid. And notice that what's going to cancel out is the milliliters of the nitric acid. And then we can keep going. I have moles of the nitric acid. In my stoichiometry, nice thing, it's always a 1-to-1 ratio. So I've got 1 mole. Well, actually, it's not always true. I'm sorry. There will be some 2-to-1 ratios in your homework. 1 mole of the KOH, that's the unknown solution, over 1 mole of my nitric acid. And the moles of the HNO3 canceled out. I now have moles of KOH. And I want you to run this calculation just to make sure you get the same thing I do. So pause the video for a moment. Okay, now come back and you should have gotten 0.00575 moles of KOH. Okay, but we're only halfway there. Well, actually, maybe 2/3 of the way there. Now, remember, if I want my concentration, remember that brackets, those brackets mean concentration. That's the moles of the KOH divided by the volume, the liters of the KOH. So, what are my moles? I just calculated that, 0.00575 moles of KOH divided by, let's divide it by our 25.0 milliliters of KOH, and then let's multiply that by 1,000 milliliters over 1 liter to cancel out my milliliters. And actually, I don't know, it's not going to come out with KOH in there, so it's okay. Milliliters. And when we come out with our final answer, again, stop the video and come back when you've done the calculation. So let's finish up this calculation. We have 0.230 molar KOH, and that is our final answer. And that's what you're going to be doing in the lab. So the homework is going to be homework 19-3, but I'm going to say this numerous times, and the lab calculations in number 1 and number 2. Okay, you're going to do those lab calculations and you're going to turn them in as part of homework 19-3, but it's also going to be part of your full lab, as you always have to do, that full lab. So please don't forget to hand in those calculations as part of the full lab. All right, so that's it for today, and I will see you next time in class.